It looks simple, a spinning metal rod, but zoom in and you'll find a precisely engineered cutting system designed to slice, clear, and survive thousands of revolutions per minute. An end mill has two main sections. The shank, the smooth upper portion, is clamped into the machine's spindle. The cutting body below is where the action happens. Running along the body are helical grooves called flutes. The sharp edges along these flutes are what actually cut the material. As the end mill spins at high speed, each cutting edge shaves off a thin layer of material called a chip. The helix angle of the flutes, typically between 30 and 45 degrees, pulls these chips upward and out of the cut zone. This chip evacuation is critical. If chips pack back into the cut, they cause heat, friction, and tool breakage. The number of flutes changes how the tool performs. Two flute end mills have larger gaps between flutes, ideal for soft materials like aluminium, where big chips need a clear escape path. 4 or more flutes leave less space but more cutting edges. Better for hard materials like steel, where smaller chips and a smoother finish are the priority. Unlike many rotary cutters, end mills can cut on the end face too, not just the sides. This allows them to plunge directly into a workpiece and then move laterally, making pockets, slots, and complex 3D contours. Center cutting end mills have cutting edges that meet at the center, enabling direct plunging. Non-center cutting types must enter from the side. Two settings define every cut: spindle speed in revolutions per minute and feed rate in millimeters per minute. Get them wrong, and the tool either rubs without cutting or bites too hard and snaps. Heat is the enemy. Cutting fluids or air blasts cool the tool and flush chips away, keeping the cutting edge sharp and the workpiece accurate. Geometry, flutes, speed, and feed. Every cut is a balance of forces working together, and when it's right, the result is perfection.